we're going to use a Poisson distribution model for x, and we're going to use, say, a mean. Well, somehow the mean of x needs to depend upon the number of units inspected going into the count for x. So we're going to have to involve k somehow, and the way we're going to do this is to say that the mean of x is k times lambda, where this lambda is some kind of a per inspection unit rate of nonconformities. Okay, that is, i.e. we'll use a Poisson k times lambda. Okay, this is the mean for x. Use the Poisson distribution with mean k times lambda as a probability distribution for x. Now, Poisson doesn't sound familiar, you need to go back and review Stat 231 facts about the Poisson probability distribution. One of the facts about the Poisson distributions that you certainly learned in Stat 231 is that the variance of a Poisson variable is the same as its mean. That is, the standard deviation for x is the square root of the mean for x. In this case, the standard deviation for x is the square root of k times lambda. If we take those two facts and think about what they tell us about u hat, that is x divided by k, well, that says that the mean for u hat is, well, it's the mean for x over k. That's k lambda over k. Oops. That is nothing but lambda. And the standard deviation for u hat is 1 over k times the standard deviation for x, and that gets me lambda over k underneath the square root. And this in turn produces standards given control limits for u hat, and they look like this. The center line for u hat, if I want to put one of those in, is going to be at this mean defect rate or mean nonconformity rate per unit lambda. The upper control limit for u hat is going to be at the mean for u hat plus 3 standard deviations for u hat. That's lambda plus 3 square roots of lambda over k, and the lower control limit for u hat is going to be that thing with a minus sign in there. That is lambda minus 3 square roots of lambda over k. C chart limits come simply by setting k always equal to 1 in those calculations. So they're simply lambda plus or minus 3 square roots of lambda. As an example, I'm going to show you in a second some artificially generated data. So these are data that I simulated from the Poisson distribution with, say, lambda equal to 2.0. Okay, so I'm secretly thinking here of, say, k to begin with always equal to 1, so we're going to have the C chart case here, and here's some U chart data. So there are 20 x's, 20 counts of nonconformities, defects that were generated from Poisson distribution with a defect rate of 2, and you can check that then, well, the center line for x, this is my u hat, since my k is always 1, at least for these first 20 samples, is going to be 2.0. So these are standards given limits. Center line will be at 2.0, and upper control limit for x, or u hat, is going to be at 2.0 plus 3 square roots of 2.0 over 1. That is, this thing is going to be at 6.24. That's 4.24 above 2. If I was to subtract 4.24 from 2, I would get something negative. So for a lower control limit for x, we'll just say that there is none. So if I apply this limit to these x's, as I look across that set of x's, there are none that's bigger than 6.24, and my conclusion here is that there is no evidence in these data of a change from the lambda equal 2.0 process standard. Let me extend this example a bit and say, well, let's suppose that an additional 5 inspection periods are added. But let's suppose now that k is not necessarily constant. And in particular, let's imagine that what we're going to add to this thing is the following. So here's an additional bit of information to this scenario. Beyond sample 20, let's suppose there's sample 21, 22, 23, 24. But now at sample 21, rather than looking at one inspection unit, I inspect 1.5 units. At sample 22, I don't inspect one inspection, I do inspect one inspection unit. At sample 23, I don't inspect one, but rather only 3/4 of a unit, 0.5 and 3. Okay, you can imagine that what I might be doing is, say, opening boxes of floor tiles and counting up pock marks. Sample 21 being 1.5 says I open 1.5 boxes. That is, I don't just open a single box, but I inspect all the tiles in 1.5 boxes. Sample 23 being 0.75 says I don't inspect an entire box, I only inspect 3/4 of a box, and so on. So with these values of k, let's imagine that I get those counts, 2, 1, 2, 1, 5, and turn them into u hats by dividing x's by k's. So I get these values for u hats. Now, what do I use for control limits for samples 21 through 25? This thing is my lambda. There is my lambda again, but now these control limits vary with the number of inspection units involved at a given period, and so we don't have simply one number for the upper control limit, but the upper control limit varies with k. You can check that in none of those cases is the lower control limit calculation where I replace the plus sign there with a minus sign. In these cases it's not positive, so in this particular example we never get a lower control limit. It's these that are then applied to those u hat values, and once again, if you apply that upper control limit to those values of u hat, you get no evidence of a process change. So there is still no evidence of a process change from this lambda of 2.0. To show you what this would look like using commercial software, here's a jump control chart for these data. Notice that this upper control limit changes period to period over those last 5 periods because the sample size, the number of inspection units, k, changes period to period. There's one other thing to say about this plot that I'm not crazy about. I would just assume that JUMP had said there is no lower control limit. That lower control limit of 0 is ambiguous. In fact, I do not wish to call those 2 points out of control points. It's not exactly clear the way they've written it how to interpret those two, but that's a fairly minor point. It is, however, how JMP does its U-charting. So be aware that that's the convention that they use. So I'd prefer to say that there is no lower control limit in this example. It's perfectly possible to have a positive lower control limit on a U-chart, but not in this particular example.